Welcome, everyone. This is the next to last class. Let's get started. Course announcements. The last class is tomorrow at 4 p.m. Montreal time. So normal time for class, not normal day, again, because there is a weird scheduling thing with McGill where tomorrow is on a Monday schedule. Office hours are at the usual time. They are not on a Monday schedule. Vincent has office hours tomorrow, and I have office hours on Friday. Are there any questions?
Yeah, I had a brief question about proving the dynamic. Sorry, this was something on Slack, so I'm not sure if it's the best time to ask this, but
probably better if it's a Slack question to keep it to Slack or bring it up at office hours again.
Okay,
if
cool.
it's a longer question about the problem set.
Okay.
I don't know if these puppies were in the water. They might just be very, very young puppies. Yeah, I hope that they're okay. They do look really wrinkly. I'm also happy to stick around for a couple of minutes after class to answer questions about the problem set if it's helpful. Let's get going. So I guess the usual disclaimer, there is going to be an entire field that we're going to be looking at way too fast. And today that's going to be deep learning. And there is obviously a lot in deep learning. We're going to be looking at a few things just as sort of teasers for what kinds of questions are being looked at in deep learning theory. So to just get a sense of the kinds of things, or some of the kinds of things that are being looked at from a mathematical perspective in deep learning. But since it is a sampler, actually that means that we're not going to be delving very much into any of them. So apologies about that. And possibly some of that is my own difficulty in getting distance from things, because this is what I work on myself. But yeah, with all that said, let's get started. So we had looked at perceptrons, and as just a review of perceptrons, a perceptron in its basic forms, there are a lot of definitions of these things. So like perceptron, you can define it with or without a bias, or you can include the taking the sign function within the perceptron or not. I mean, these are just like, I'm giving you sort of fuzzy definitions, or definitions where you could equally well be taking another definition. And when we get to neural networks, likewise, there will be other ways to define a multi-layer perceptron. So perceptron is basically a function, just a function which is weight vector dotted with input vector. And the goal of the perceptron is to pick your weight vector such that if you have a data set of points, where some of them are labeled +1 and some of them are labeled -1, the function is going to be greater than 0 if the data point is labeled +1 and less than 0 if the data point is labeled -1. So you're trying to come up with basically a hyperplane that cuts your data points so that everything on one side is +1 and everything on the other side is -1. And we can find the weight vector W, or a weight vector W, that works via this iterative algorithm, the perceptron learning rule, where we change the weights to fix particular data points that were misclassified. So the goal is to find, again, a hyperplane like this, where everything on one side is the +1s and everything on the other side is the -1s. But it only works if the data points are actually linearly separable at the start. Otherwise, the perceptron learning algorithm might not work. So one can ask, what if the points are not linearly separable, which is basically the case for most circumstances? One could also ask, what if you're not trying to do binary classification? What if you're trying to do something more complex than that? And so that's one of the motivations for things that are more complex than just perceptrons. There was one of the early iterations of of artificial intelligence was people thinking, oh, let's just do everything with perceptrons. And it turns out that doesn't work very well. There was a famous example where people thought that they had worked out that you could use a perceptron to linearly classify Soviet and American tanks, distinguish between the two. It turned out that the reason why these were linearly separable was because one set of photos was taken during the day and the other set was taken during the night. And so this was a really early example of overfitting to a training data set where it was not actually working out the differences between the tanks, it was working out the differences between the lighting. And that was linearly separable. But a surprising number of things are linearly separable. Like, for example, MNIST, you can, if you know the MNIST data set, you can get like 93, 95% accuracy with just a perceptron. It's one of the reasons why MNIST is not a very good data set from many perspectives. Anyway, but we eventually realized there are many problems which are not linearly separable. And so there are more sophisticated methods which are not limited to deep learning, but we are today going to look at deep learning. So neural networks in general are computational models which are loosely inspired by the brain. And we're going to look at deep learning and specifically feed-forward fully connected networks today. So there are a lot of different kinds of neural networks, and not all of them are even like this kind of computational model. There are many different computational models. But overall, neural networks are computational models loosely inspired by the brain, where the basic idea is that you have many simple computational units that perform complex computations by interacting. So you have a lot of very simple things that together give you some complicated emergent behavior. And in the brain, these are called neurons or nerve cells. But in a mathematical or computational sense, we're going to abstract away from nerve cells and have simple computational units, which are sort of mathematical functions, which are very simple. And by combining many simple functions, you get a bigger overall function or bigger overall emergent behavior. And again, there are lots of different kinds of artificial neural networks. If you're interested in something totally different, you can look up Hopfield networks or attractor networks, which are a different computational model. They're basically a whole bunch of perceptrons which are all connected to each other and all serve as perceptrons with respect to each other and are a model for how memories in the brain work. But we're going to look at something different. There's a question. Could you explain why MNIST is linearly separable quickly? Didn't know that. MNIST is not completely linearly separable, but basically MNIST has a lot of, so MNIST, for those who haven't seen it, is a digit recognition data set. So it's like distinguish a handwritten 9 from a handwritten 4. And basically there are just so many pixels in MNIST. The number of pixels in MNIST is way more than you really would need to be able to classify these digits. And so with all that redundancy, you can work out a lot of correlations that get you almost all the way there. Now, there are some digits that are a little bit less conventional. You know, those edge cases are why you actually can do really well with convolutional neural networks, but there isn't a need for them for most of the cases. Yeah, I don't remember, but you know, somewhere between 90 and 95% accuracy you can get, I believe, with just perceptrons. Okay. So let's move on to actually multiple perceptrons interacting in a neural network. Oh, and by the way, with MNIST, you cannot learn it with the perceptron learning rule because it's not exactly linearly separable. So you have to learn it with something like gradient descent, which we're going to look at. You can pretend it's a deep neural network, learn it with gradient descent, and then actually, even if it's just a perceptron, you can do pretty well. Okay, each biological neuron, like neurons that are literally in the brain, just as some background here, is composed of different things. So it has dendrites, which are basically to collect signals from other neurons. It has a cell body that integrates those different signals coming from other neurons, and there's an axon that, depending on the inputs that it has received, can then send a signal to other neurons. And the way that all these neurons communicate is electrically. They send literally electrical impulses. So these dendrites are collecting electrical signals from other neurons. Then all of these dendrites feed into the central cell body, and then the cell body basically decides, did I get enough input? If I did get enough input, then I'm going to send a signal along this axon, and then whatever neurons are receiving from this axon, there are some branches coming out here, will get a signal. And there are a lot of these neurons, like billions of them, in the brain. And so together, this neuron will send to some others, and this neuron will send to some others, and so on. And you can have like tens of thousands of connections per neuron. OK. Are there questions about the biological model of neurons? Or just the biological structure, I guess, in this case? I'm glossing over a lot of the details here. Individual biological neurons are way more complex than artificial neurons. Overall, the result is that in your whole brain, you have many neurons that are firing together in different patterns, and those patterns will lead to other neurons firing in different patterns, and those patterns will in turn lead to more patterns. And it is this self-perpetuating system that leads to thoughts and also takes in inputs from the outside world. And also leads to outputs like moving my hands around and stuff. So a perceptron is a simple model for an individual biological neuron. It is not a very good model, but it is a first order, a first cut at a model. So the idea is that if a linear combination of the inputs coming into a perceptron is large enough, sorry, if a linear combination of the inputs coming into a biological neuron is large enough, then the neuron fires. Otherwise, it just doesn't do anything. So this is similar to what's going on with a perceptron, where you have your inputs and you take a weighted combination of them, a linear combination of them, and you say, OK, is it big enough? If so, I send a signal. If not, I don't. Now, what we were looking at was the situation where if this was positive, then I send one signal, and if it was negative, then I send another signal. More generally, you can imagine a perceptron with a threshold or a bias. So we've added now this sort of constant term. And we say that it does one thing if w.x minus b is greater than 0, and w.x minus another thing if w.x minus b is less than 0. Again, what we were looking at before was just b equals 0. So it does one thing if w.x is greater than 0, it does another thing if w.x is less than 0. So what we were looking at is just a special case of this where the threshold is set to 0. Now, for biological neurons, there actually is a threshold. Like if the signals coming in combine to go over a threshold, that neuron decides, I'm going to fire. And specifically how it works is there are these voltage-gated ion channels. I realize this is more chemistry than probably people wanted in a CS class. But basically, if the input electrical signal is big enough, then the neuron suddenly starts letting in some ions, so some charged particles. It lets some ions into the cell, it lets other ions out of the cell, and all of these things depend upon the voltage currently in the cell. So the voltage in the cell depended upon the inputs that the cell got. And when the voltage reaches a certain point, the threshold, then suddenly the neuron triggers what's called depolarization. So some ions go in, some ions go out, and suddenly there's an electrical signal that propagates throughout the entire neuron. And it is somewhat like a switch. Like either it has reached the threshold or it hasn't reached the threshold. Now, this is still a somewhat simple model. Biological neurons do all kinds of things, like they send bursts of signals. It's not an exact threshold, and this linear combination of inputs is definitely a simplification. It's not a linear combination of inputs in biological neurons. It's something much more complex than that. But this is a simple model of how a biological neuron actually works. Are there any questions about this? This is as much chemistry and biology as we're going to get to today. The point of artificial neural networks from a computer science perspective is generally not to model the brain. It is to get inspiration from the brain so that we can do cool things. Now, in computational neuroscience, sometimes people are using artificial neural networks to model the brain, but I'm not pretending that what we're doing now is a good model for the brain. It's just a good model for getting good CS results. Okay, so we can generalize this model, which we just saw. So here we had that the neuron fires, so that at the output is 1 if this linear combination is greater than the threshold. Otherwise, it outputs 0. You can generalize it to some nonlinear function of this. You can say that instead of being literally a step function where it's either 0 unless it reaches a certain point, in that point it's 1, you can say, OK, well, it's going to be a nonlinear function which does something depending upon where I am here. So you could make it be, for example, a sigmoid, where instead, previously what we were doing is we were saying, if it's below the threshold, it's 0. If it's above the threshold, it's 1. But you can soften that. You can say, if it's below the threshold, it's 0, but then it sort of increases gradually up to 1. And the way to make that formal is to, often people will use the sigmoid function. So this is 1 over 1 plus e to the negative z, which is just a way to graph this, which starts out at 0 and then goes up to 1. Another way to do this is instead of saying we're going to be 0 and then gradually go up to 1 and then be at 1, is we could say we're going to be at 0 and then we're suddenly going to just go up linearly and not stop at 1 at all. And we will get to why people might do this. So this is called a sigmoid, and this is called the ReLU. And ReLUs are maybe not as good a model for actual neurons, except in some cases there is reason to believe that this could be reasonable biologically. But they're certainly good from a computational perspective, and we'll see a couple of reasons why that's the case for ReLUs. But again, in this case, each perceptron is saying, OK, I'm going to take a linear combination of my inputs, and I'm going to subtract the bias from it. And then I'm going to throw that into a ReLU function. And so the ReLU function is going to say, again, the ReLU function is max of 0 and z. So it looks like this. If I am negative, then I output 0. If I am positive, then I just don't do anything. I output the input. Yeah, so we will see a couple of reasons why ReLU is useful. Questions? OK. So let's take a look at multilayer perceptrons in a simple version of an artificial neural network. So inspired by the brain, we can combine many perceptrons according to a weighted graph. So the weighted graph is one way to think about an artificial neural network, or this particular kind of artificial neural network. It is not the only way to do it, but it's a neat visualization. And so what the idea basically is with the weighted graph is that here we saw a perceptron being like this neuron which takes in these inputs and gives an output. Here we're going to see each of these things is itself a perceptron, which takes in these as inputs and gives an output to all of the things down there. So this is another perceptron that takes everything here as an input and then gives outputs to everything down here. This is a perceptron that takes everything here as inputs and gives outputs to everything down there. So basically, each time you move through, each of these edges is implicitly directed, and it is saying this gives input to this. This also gives input to this, and all of the inputs get linearly combined. And then there is something that happens at this particular node in the graph, which represents a neuron or a perceptron, and then it sends the answer downstream to the things in the next layer of the network. I'm glossing over a bunch of things. So this is assuming that the graph is arranged in layers, which is not always the case. So here you have a layer of inputs. So these are all the inputs. These are the neurons that get input from the inputs directly. This is one layer. This is the next layer. Layer number 2 gets input from layer number 1. Layer number 3 gets input from layer number 2. But the neurons might not be arranged in such a nice layered way. You could have connections from here to here, what are called skip connections, or you could have connections circling back. Anyway, that's the intuition. Let's see what it actually translates to mathematically. So we can define a multi-layer perceptron, or a fully connected network, fully connected feed-forward network, if you like. It's a particular kind of function from inputs to outputs. And I'm just going to use some notation for the dimensions to make it clear like what the dimension of different parts of the network is. So this is a recursively defined function that computes its output according to various intermediates called hidden layers. So here's a lot of math. Let's see what happens. So we have here a remember, it's taking inputs if there are vectors with dimension n in, so n input. And the first hidden layer is these neurons here. And each of these neurons is computing a linear combination of the inputs, and then computing subtracting a bias or a threshold, and then taking a nonlinear function from it, nonlinear function of it. So this is given a particular nonlinear function. We're going to take our vector of inputs here, and we're going to compute linear combinations at each of these neurons. And that corresponds to taking a matrix multiplication by some matrix W1. So W1 is a matrix in N1 by N in. And so you multiply that by your vector X in R N in. So it's an N in dimensional vector that becomes an N1 dimensional vector once you've multiplied it by this matrix. And that gives you the activations here, except you also need to subtract the bias. And then you need to apply a nonlinear function. So if you think about what's happening at each one of these, each of these is an entry in the vector h1. So each of these, there are n1 of these. And each of these is saying, OK, I'm going to take a linear combination of my inputs. So this is a linear combination of the inputs. I'm going to subtract a bias here. And then I'm going to take a nonlinear function of that. And the reason why you can write it in this matrix notation is because we're doing it for all of these entries of the vector simultaneously. So we can write all of these perceptrons together as a matrix multiplication times the input vector minus a bias vector where there is a particular bias at each one of these neurons, and those neurons maybe have different biases. So this hidden layer is just each one of these is a perceptron, and each of these is an entry in this vector h1. H2 is doing the same thing, only instead of taking inputs from X, it's taking inputs from H1, so the first hidden layer. So instead of taking, it takes inputs from the things that were computed already with respect to the inputs. And it has a new weight matrix, which is a weight matrix of N2 by N1, because that needs to be multiplied by H1, which is a vector of dimension N1. So just making sure that all dimensions line up. Here we have an output in that is N2 dimensional. And then we get a hidden layer of size N3 and all the way down to the dth hidden layer, where D is often called the depth of the network. And here we have the dth hidden layer is computing, again, perceptrons with respect to the D minus first hidden layer. And then finally, we have an output layer that is just doing the same thing. Sometimes the output layer might not have an activation function sigma, and sometimes it might not have a bias. But this is just sort of a general way of framing it to make it a bit simpler to think about. Are there any questions about this? I realize some of you may have seen this before. If you haven't seen it before, I realize it also may be a lot to take in. This is a way to write a function. It's a function from inputs, which are vectors, to outputs, which are also vectors. And the way it computes its output is by computing all these intermediate vectors, which are called hidden layers. So each of these hidden layers is just a vector of perceptrons applied to the previous layer. Any questions? If you left out all of these sigmas or made them be linear functions, what would happen? You would have a linear function of the inputs for your first hidden layer, and then you take a linear function of a linear function. But if you do repeated linear functions, you're going to end up with another linear function. So if you left this out, then the entire thing would just be equivalent to a single matrix multiplication and a single bias. For one slight note is that, this is just a slight note for those who want to delve in a bit more here. It is not totally unreasonable to use a deep linear network. And I realize this sounds really weird if you have not seen this before, but given the way in which one trains a deep nonlinear network, one can do the same thing for a deep linear network, and it will give a different result depending on how you've parameterized it. So even though a 10-layer neural network you might be able to write it as a 1-layer neural network because it's linear. If you perform the kind of learning algorithm, which we'll see in a few slides, if you do that for a 10-layer network, you will get a different result than if you did it with a 1-layer neural network, even if they started out in the same place, as it were. And in fact, you can think of a deep neural network as performing regularized regression. There is an implicit regularization by making it be deep. I'm happy to talk about that more later. But yes, in answer to the question, it still cannot model nonlinearities. You're still performing linear regression. It's just a form of regularized linear regression. I'll talk about it later if there's time. OK, so here's an example. Let's compute the output of this multi-layer perceptron at this particular input point. So if you take this input point, how do we compute the hidden layer? Well, we're going to multiply it by the first weight vector. Then we're going to add the bias vector. Oops, sorry. So here's the first hidden layer. We're going to multiply x by w1. And then we're going to subtract the bias vector. And then we're going to apply our nonlinear function. So if we're using the nonlinear function ReLU, then we have ReLU of w1 times x. You can compute this this matrix times this vector is going to be 2, 0, 0, 0, if I did the math correctly. And then you subtract the bias here, which is this vector here. And so you have ReLU of this. And that's ReLU of 1, negative 1, negative 1, negative 1. You can think of the hidden, you can think of this as filling in 1 is this one, negative 1, negative 1, negative 1, except that now you need to compute the ReLU at each of these neurons. And so ReLU of 1 is max of 0 and 1, which is 1. ReLU of negative 1 is max of 0 and negative 1, which is 0. So what ReLU does is, again, it turns negative things into zeros, and it turns positive things into just keeping them the same. So the 1 stays a 1. The negative 1, since they're negative, becomes zeros. So now, again, what we did is we multiplied our input by the first weight matrix. We subtracted the bias vector. And then we hit it with a ReLU. By the way, a note, sometimes people will write neurons as computing with adding the bias vector. Depending upon your convention, it can be adding or subtracting. I'm using subtracting because it's sort of the neuroscience-y way to think about this as a threshold, but sometimes you'll see it written as an addition. Make sure if you're doing math with it that you know that you are consistent. It doesn't matter which one it is because you could just take the negative of the bias vector, but make sure you are consistent. OK, so that was the first hidden layer. I guess in this case, we only have one hidden layer. Now let's compute the output layer. So here we take this hidden layer h1. We multiply it by the second weight matrix. So this is a second weight matrix. Let's multiply this vector by this matrix. And we're going to get negative 1, 0. Now we subtract the bias vector for the second bias vector. And so if we subtract that, then we get this minus this, which is 0, 1. Now, ReLU of 0, 1 is just 0, 1 because 0 goes to 0 and 1 goes to 1 in the ReLU. So that is our final output if we took this 1, 0, 0 as input in this particular network with this particular setting of the weights and biases, we would get 0, 1 as our output. Other questions? Why is having a minus more compatible with neuroscience? Great question. So it's basically because in neuroscience, a bias is thought of as a literal threshold. So if you are above the threshold, which is like a voltage threshold, then the neuron fires. But you'll see it written both ways. More questions? Okay. So how do you actually use neural networks? So we often use neural networks to approximate functions of observed data. And you can think of a neural network as a function approximator, basically. So for example, we saw classification problems before, where we have some data points, which are n-dimensional vectors, and we have labels, which are in some set. So for example, if you were classifying images, if these were image vectors, then you could have the labels be like dog or cat or book or so on. So we want to learn a function f that approximates the function that we've observed from the data. So f of x1 is approximately y. Sorry, f of xi is approximately yi for each of the examples. So one way to do this is to write down a neural network that computes such a function. So typically, the way we're going to find such a neural network is we're going to fix the structure, or the architecture, which is just fix the graph. So if you go back to this picture, this is the structure. If we don't know what the weights and the biases are, this is the structure where you say 3, 4, 2. That's our structure. And activation function, so in this case, it would be ReLU. And then we change the weights and the biases to fit the data. And the weights are just the W matrices before, and the biases are the B vectors. And so, yeah, we change the weights and the biases to create a function that best replicates the patterns we have seen in the data. Now, how do we do that? So we can think of there being some big vector where we've just thrown all the parameters we are learning. So we have these W matrices, these weight matrices, and we have these vectors, these bias vectors B. And let's just turn all of them into a giant vector. You can turn a matrix into a vector just by vectorizing it, just by putting all of the entries in a row. You just think of theta as capturing all of the parameters that we are changing. So then the function the neural networks is computing will actually depend upon theta. And let's change our notation. Let's write it as f sub theta of x. So f depends upon theta, the parameters. And so we want to change theta so that we get a function that approximates the data points, and what we've observed as our data. So for example, in our network with one hidden layer, if we increased the final bias vector, we would increase the output. And it's just if there's one hidden layer, if you increase the output bias, you increase the output of the network. So that would be an easy way to change theta to change the final function. Maybe increasing the output is a way to better approximate the data that we're observing. Changing individual entries of a weight matrix is going to change the function in more subtle ways. But changing the individual weights is going to affect the function that's computed by the network, and that could be good, depending on how you want to fit your data. So that's, again, we can change individual parameters within the network in order to fit our data better. So how do we pick theta? The perceptron rule is unfortunately not going to work here. because we have many perceptrons. We can't learn them all at once with the perceptron learning. What are some ways? There are, in fact, many ways to do this. The way that is most popular now is to use gradient descent, which is why we were talking about gradient descent last time. But there are other ways. So we can find a good set of parameters theta by using gradient descent. And then here it's a really important thing to recognize what we are doing gradient descent on. So what is the thing we want to minimize? If you're doing gradient descent, you need to know what you're minimizing and what variables you're changing in order to minimize it. What is the thing you're trying to minimize? A loss. So we need to define what a loss means. So we want to minimize the difference between the predicted output of the network and the true observed output for your data, for each data point. And so we can write down a loss function that is 0 if the two things are equal. One natural loss function might be just take the difference of them and take the L2 norm, the squared L2 norm. So that in particular, you want a loss function to be 0 if you've correctly predicted something, right? You also actually, sorry, I guess I should have said, you also want the loss function to be, you want various other properties of the loss function. In particular, you want it to be greater than 0 if they aren't equal. So you want to decrease the loss function so it's 0, and when it's 0, you want the things to be the same. Okay. So then we want to minimize this loss function. And what do we want to change here? What are the things that we are, the variables that we are changing in order to perform the gradient descent? Because gradient descent means changing some variables. Yeah. So we want to change the parameters of the network. And so typically that means changing the things we captured in theta. So this is weird because this loss function depends upon the data, but it also depends upon the theta. That rhymes. That's cool. It depends upon the data, but it also depends upon the theta. So we need to pick the right theta. And the data is actually fixed. We've observed the data. So we're not doing gradient descent on the data. If you did gradient descent on the data, you would end up doing what's called deep dream, and you would end up hallucinating new data based upon what you would like to see in your output. And that's pretty cool. But that is not what we're doing now. So if you do gradient descent with respect to theta, you are trying to minimize this loss as a function of theta, basically. So that means we need to calculate the gradient with respect to theta. And that means we need to calculate the partial derivative of this with respect to each particular parameter theta j in our vector theta. Okay, so let's see how we can do that. So let's do it for a perceptron in particular. In a perceptron, we have the function. Let's just assume it's a single perceptron, so the output is actually a univariate output. So we have just a vector x. We multiply it by another vector. We dot product it with another vector, and then we subtract a single constant bias. So let's see how gradient descent would work here. The parameters are the entries of W and the bias. So we want to be able to change both the bias and the entries of W. So let's work out the gradients. But first, we can suppose a particular loss function. And in this case, let's use the loss function that we were looking at before, which is just the squared L2 norm. In this particular case, since this is it's a univariate output, the L2 norm is just the thing squared. So again, if you have a vector with just one entry, then the L2 norm of the squared L2 norm is just the square of that one entry. This is our loss. It's just the difference between what we predicted and what we observed squared. Let's compute the derivatives. So here's the derivative with respect to b. We can differentiate this loss function. And we can say, OK, well, we're going to use the chain rule. Sorry for this is painful. 2 times the thing inside the square times the derivative of the thing inside the square. So here's the derivative of this sigma. But then we also need to take the derivative of the thing inside the sigma. So we're doing the chain rule twice. We're saying this is the derivative of the square of this thing. This is the derivative of the sigma part inside here. And then we need to take the derivative of what's inside the sigma, which is partial with respect to b of this. And this is just -1. Because this the only part of this that depends upon b is negative b. And the derivative of negative b with respect to b is just -1. So that becomes -2 times this times derivative of sigma here. Questions about that? Let's see the other computation, the derivative with respect to the weights. The question here is the output of f theta for this function scalar. For this particular one, we're doing a single perceptron, so it is scalar, yes. That's why our loss function is a loss function with respect to scalars. It's not, there are no vectors here. Or sorry, this and this are both scalars. The input xi is a vector. So now let's take the derivative with respect to wj, which is another parameter. So again, the parameters we need to take derivatives with respect to are the entries of the weight vector and this bias constant. So we already did the bias. Now let's do the weight vector. It's just the same thing, only when we get to this part, we're doing the chain rule again here. But when we get to this part, we're taking the derivative instead of with respect to b, we're taking the derivative with respect to wj. Now, what is the derivative of this with respect to wj? The only part of this that depends upon wj is the part where it's wj times the jth entry of xi. So that is a linear function of wj. I realize this is a little bit hard to wrap your head around because you thinking of this, it's a linear function of x, but it's also a linear function of w. And so if you take the derivative with respect to w, you get the coefficient of w here, which is just the corresponding entry of the vector x, which is xi in the entry j. So this is the derivative of the loss function with respect to the weight wj. This is for a single neuron, a single perceptron. Are there questions about this? Fortunately, there are deep learning libraries that don't require you to do any of this, but it's good to know what is going on under the hood. OK, so that is how we would calculate the gradient for a single parameter of the network, how that parameter affects the output. Sorry, the derivative of the loss with respect to a particular parameter. The gradient is composed of those partial derivatives. So there is this thing called backpropagation. What is backpropagation? Well, it's just using the chain rule to work out the gradients with respect to every parameter of the network. When we worked out the parameters of individual perceptrons, which basically corresponds to working out, if you forgot about the rest of the network over here, if you just looked at one of these and you looked at the gradients of the loss here with respect to this. Now, there is a way to calculate the gradients of everything in this network pretty fast. And the way you do it is by working out we're trying to work out the gradients. So for each of these edges here, there is a weight. Remember, there's a weight. This means this thing depends upon these inputs, and for each of them, there is a weight associated to it. So for each of these edges, there is a weight, and for each of these nodes, there is a bias. And we want to work out the derivative of the loss with respect to each of the edge weights and with respect to each of the node biases, basically. And I'm not going to go into the details of it, but this thing is called backpropagation. You basically work out the gradients with respect to everything in the last layer. So all of these weights, gradients of the loss with respect to all of these weights. And that's pretty easy because in just the same way as we saw, these things depend directly upon these weights. So if you increase this, you're going to affect the output in a very predictable way. It's very easy to compute the derivative of the output with respect to this weight. Now, once you've worked out the derivative with respect to these weights, you can work out the derivative with respect to these weights by using the chain rule, because the way in which this weight affects the output depends upon the derivative of these weights. So once you've worked out these, you can work out these. Once you've worked out these, you can work out these. And if this reminds you of something, it's because it is actually dynamic programming. Backpropagation is a form of dynamic programming where you do something very efficiently by storing all of these gradients, then storing all of these gradients, then storing all of these gradients, and by computing them in the correct order, you can save yourself a lot of computational power. So you can actually compute all of the gradients quite efficiently. Other questions? Okay. So again, the overall learning algorithm is we pick a structure and activation functions for the network. We pick some starting parameters. This is always how it works in gradient descent. Pick some starting place. Typically, that's random. And there are all kinds of good ways to choose how to randomly initialize your network. You update the weights and biases by gradient descent until you have your output being approximately your input for all of the data points. This is a huge simplification, but this is basically how deep learning works. And I should note that even for a perceptron, gradient descent can be better than the perceptron learning rule because, for example, the data might not be linearly separable. And the perceptron learning rule will work if the data is linearly separable, but if it's not perfectly linearly separable, then it might fail completely. Gradient descent might be a good way to do learning even for a single perceptron. There's a question about dropout, which I'm not going to talk about. I'm sorry. I'm happy to talk about that separately in Slack. So why does deep learning work? So last time, we saw that gradient descent works well with convex functions since all local minima are global minima. We are performing gradient descent on theta to minimize this loss function. Is this a convex function of theta? Does the loss function depend? So this is the loss function. How is the loss function affected by the parameters of the network? Is it a convex function of the parameters? Generally not, no. Neural network optimization is almost never convex. Okay, so why does it still work? So two reasons why this isn't a huge problem. First, and I'm going to be a bit hand-wavy here. I'm not going to go into proofs, partly because in not all of these cases are there actual proofs. In some cases, there are some proofs. So first, you are actually usually close to a global minimum in deep learning. And second, for a lot of the local minima, they actually are global minima, even though the function isn't convex. So you don't have that guarantee, but oftentimes the local minima are global minima. So intuition for the first one, why the first one is true. So the intuition for the first is that there are many global minima because there are just tons of parameters. So there is a lot of redundancy. Oftentimes, you can get your loss function down as low as you want without changing your weights very much. And this is something which people observe in practice, that the weights you start with are pretty close to the weights you end with. The intuition for the second is that given that you have so many parameters, generally there's some parameter you can change to decrease the loss, unless you're truly at a global minimum. There's a formal way to think about this as like eigenvalues of the Hessian, but I'm not going to go into that. However, we still don't really know why deep learning works so well. Questions? Let me keep on going for a bit, just to give some more intuition for some cool things in deep learning theory. So we saw last time that there are flat regions sometimes in gradient descent. And what a flat region is basically a place where the gradient is very low. So you are not getting very much signal. Even if there's a really good place for you to be over here, you can't get there very fast. This is a huge problem in deep learning. For example, this is a neural network that you can write down that expresses the sawtooth function. So this is the sawtooth function. It's a function from one input variable to one output variable. And the function goes like this. And this is a neural network. So I'm writing it down for you. If you could find this neural network, you would be able to express the sawtooth function. If you could set the weights perfectly, it would work. But unless you're already close, the gradient is very low. So this is what this looks like, I think. And there's been some work on this. As far as I understand it, the loss function looks like a really deep energy well, a really deep well. But unless you're very close to it, unless the parameters are already very close, the gradients are very flat. So if you are more than a small distance away from the correct network, you're never going to find the correct network, even though it exists. So this is an evil example, but it's a pretty simple evil example. The loss function here is you're trying to create the sawtooth. So the loss function is the difference from the sawtooth. If the loss function is like the L2 distance from the sawtooth, for example. The sawtooth is just like, this is a function from inputs to outputs. So you can think of it as XOR. It's like the parity. It's like the parity function. It's trying to work out, it's alternating between 0 and 1, going up and down many times on the interval between 0 and 1. If you're trying to learn XOR, it's really hard. And then finally, I'm going to close by talking about how does it relate to the loss landscape. So the loss landscape basically looks like this. Unless you are if you are, what you should imagine in the loss landscape, when you're seeing plots of loss landscapes for deep learning, the variables, the dimension of the space in which you are in, is the number of parameters of the network. So this is a picture of the number of the parameters of the network. And if you set the parameters exactly to these, then you are in this very low loss situation where you are exactly capturing the sawtooth. But if you are far away from that, then you are in a very flat area. And so changing our parameters doesn't really do anything. And so you have very low gradient. This is not actually a picture of this. This is a picture of another function. But this is my understanding for what this particular loss function looks like, loss landscape looks like. If you're far away from this setting of the weights, then you have very low gradient. And then finally, I want to touch on activation functions. And there's more that I'm happy to discuss in the Slack. I mean, I work on deep learning theory in my research. So which activation functions do we pick? I sort of promised to give an intuition for ReLU versus sigmoid. So remember in the gradient computation, we got this. We had sigma prime, so the derivative of sigma, the activation function. Now, if this is close to 0, then all our gradients vanish. And we really don't want all our gradients to vanish, or at least we don't want them to vanish everywhere. So this is why some people will often use the ReLU, even though in some sense the sigmoid is maybe a better model for what could be going on in biological neurons. The ReLU is better because of this issue. So if you look at this function, the derivative is 0-ish. It's very close to 0 if you're over here. So anything greater than like 4, it's close to 0. And if you're anything greater than like less than like -4, it's close to 0. So only in the small region is this going to be anything other than basically 0. So if you're trying to learn, you're often going to be in the situation where this thing vanishes. So you don't really like this. You basically want something where the derivative is always something less than, or is a significant amount of the time the derivative is non-zero. Now for ReLU, the derivative, if you calculate the derivative of ReLU, it's 0 here, but it's 1 here. The ReLU is 0 up until the derivative is 0 up until you get to 0, and then it's 1 because it's just again ReLU is max of 0 and z. And the derivative is not defined here, but there's 0 probability that you actually hit this cusp point. So then why does the ReLU make this better? Well, because if you have negative inputs to a particular neuron, then the derivative is 0, but typically that occurs for only about half the neurons. So for any given data point, you will have non-zero gradients at half the neurons or half the weights of the network. And so you'll be able to learn for half the weights, which is all you need. And those half of the weights will be different for different data points. So as you vary over your entire data set, you will be able to get learning signal for all of your weights, essentially. The other reason why people use ReLU is it's just a lot easier to compute. You don't have to compute derivatives of an exponential function, I think. I mean, it sort of makes sense. The math is just a lot easier if you're computing derivatives of this piecewise linear thing. OK, I'm happy to stick around for questions. Sorry that I couldn't go more deeply into details of other parts of deep learning theory, like generalization, memorization, expressivity. There's a lot of cool stuff here. Here's a poll about the speed of class. Next time, we will finish by talking about cool unsolved problems in math and about paradoxes or seeming paradoxes.